general term would be given to us, and indirect one is the one that a sequence would be defined recursively, and you have to list some members, okay? So this is going to be number one, and you want to list 5 members of each sequence, okay? You want to write the first 5 terms. The first 5 terms of a sequence. We need it for future, and we've been working with the sequence, so why not we try it? So I do a couple of them. If we get time, we come back and we repeat it. There are 2 types. Let's try, see if we can do all of them. So we get the idea. The type 1 is a straightforward. An is given to, this is a -1 to n over n, and n is a counting number. Even if they don't say anything, you are going to consider the n, but 1, 2, 3, etc. Okay, 5 numbers. Replace n by 1 like a function and find the solution right away. Okay, so the first one, a1, is going to be -1 to the first power is a -1 over 1, the result -1. So the first term of the sequence is -1, and we're done. Question. Second term, a2. a2 would be -1 squared over 2. -1 squared is 1, 1/2. So the second term is going to be 1/2, and we're done. Okay, a3 is going to be -1 to third, okay, to the third over 3, because you replaced n by 3. So that gives -1/3. So your third term is going to be -1/3, and it's done. To the fourth one is going to be -1 to the fourth, okay, over 4, which is going to be a quarter. So the a4 is going to be a quarter. Okay, and the a5 is a -1 to the 5th over 5. So that gives -1/5. So the a5 is going to be -1/5, and you're done. You see, that's a 5 term of the sequence, -1. You don't have to rewrite it. 1/2, -1/3, a quarter, and a -1/5. 5 terms of the sequence. Any question? So that's a type 1. The type 1, the terms are directly given to you. Okay, the type 2 is going to be when the terms are not going to be given to you. So I don't have the b now here. I'm not going to do the b. Okay, b is easy. You just check this again. bn equal to the 2 to the n minus 1 plus 3. So just substitute the numbers and you get it. Okay, if I get time, I come back and do it. Otherwise, I finish this one, I will post it. Okay, so that's part B. So let's go to the C. C is type 2. The type 2, you got to be careful. Some people miss this one. We call it recursively defined. We are going to have 2 sections on these sequences after your test. Okay, so a general term would be given in terms of some of its prior terms or previous terms. In this case, Cn is twice of the Cn minus 1, the previous term. Okay, then minus 1. And then one term would be given, we call it initial step. C1 is given. So you already got one of the terms. We asked for the 5, so this is the C1. You have to find the C2, 3, 4, and 5. Okay, so each term is twice of the previous one, then minus 1. So solution. You start with the given one. C1 is already given, is equal to 2. So we're done with the first one. Okay, we want to find the C2. C2 is equal to, you see, twice of Cn minus 1. Twice of the previous term, because if you replace the n by 2, 2 minus 1 give you 1. So it's a 2C1. 2C1, then minus 1. Okay, now you substitute. C1 is 2. 2 times 2 minus 1. 4 minus 1, 3. So C2 is equal to 3. That is the second term. Any question? It's like the function. You substitute, but you take you back. You say 2n. 2 minus 1 would be c1. So 2c1. So you go, you have the c1. You substitute to get the result. Okay, are you ready for the c3? c3. This means you put the n equal to 3. So 1 done would be c2. So it's going to be 2 times c2 minus 1 is equal to the 2 times c2. c2 is 3. 2 times 3 minus 1 is going to be 6 minus 1, which is equal to 5. So c3 is equal to 5. That is the third term. Any question? c4. c4 is twice of the c1 done. That's 4 would be 3. Minus 1. 2 times c3. c3 is 5 minus 1. 10 minus 1, which is a 9. So c4 is equal to 9. That's a c4. One more. c5. c5 is 2c4 minus 1. It's a 2 times c4 is 9 minus 1. 18 minus 1, 17. 17. So the terms 2, 3, 5, 9, 17, etc. And you're done with the 5 terms. Any question? So be careful about this group. Give you one more of this group, and this next one is the one like the one that we're doing with the strong induction. Okay, part D. What is the sequence? AN is twice of the previous one plus 3 the previous one again. 3AN minus 2. Okay, it's a combination of 2 previous terms, if you like. Got to be careful. In this case, they have to give you 2 initial conditions. It's like the strong induction. So you are given that the A1 is equal to 2, A2 is equal to 3. So you already got 2 terms. You need 3 more. Okay, we asked for the 5. So 1, 2, 3, 4, 5. Then you're done. Okay, are you ready? There you are. I've already got the first one. A1 is 2. So this is one of them. So we have the second one. Okay, so we start with the 3 because you already got the 2. A3, replace the n by 3. A3 equal to twice of A1 done, n minus 1. Your n is 3, so that gives you 2. Plus 3A2 done. Remember, your n is 3. Your n is 3, so 2 done, that gives you 3 minus 2, which is 1. Any question? We substitute, but we don't usually write it down. Okay, your n is equal to 3, so that gives A3. 3 minus 1 would be 2. 3 minus 2 would be 1. Now substitute, you have the A1 and the A2. So it's going to be equal to, okay, it's going to be 2 times. I just identify that we did substitute. It's going to be 2 times 2 because we have the, 2 times 3 because the A3 is, they said 2 times 3 plus, it's going to be 3 times A1, and your A1 is equal to 2. A1 is equal to 2. Okay, you go back and you take these numbers from there. So that make it to the 6 plus 6, which is 12. So A3 is 12. Okay, that's going to be 1. Double check because this number is going to be useful. It's going to be useful for the next one. So double check, make sure that you have the correct answer because it would affect the other terms as we go on. Okay, so everything's all right. So that was the A3. We go to the A4. A4. A4, replace the n by 4. It's going to be 2, 1 done. A3 plus 3, 1 more done. It means 2 done. That gives A2. Okay, so it's going to be equal to the 2 times A3. A3 is 12 plus 3 times A2. A2 is 3. Okay, so that gives you 24 and 9. So that give you 33. Okay, so A4 is 33. Any question? A4, one more. Replace the n by 5 to get your n A5. Okay, so A5 is equal to 2 times 1 done, which is going to be A4. Okay, plus 3 times 1 more done, or 2 done. 2 done, that give you A3. Okay, so that would be A3. Okay, now we substitute, it's going to be 2 times A4. 2 times A4 would be 33. Okay, plus 3 times A3, which is 12. Okay, now 2 times 33 would be 66. Okay, and this is going to be 36. So it's going to be 12, I think 102. Yes, that's it. So that would be A5. So A5 is going to be 102, 102. So the terms of the sequence going to be 2, 3, 2, 3, 12, 2, 3, 12, 33. Okay, 33 and 102. These are going to be 5 terms of the sequence. This is very popular case. All of them, we are going to have 2 kind of application problems when we get to the next quiz. For both of them, you have to apply, you have to write a couple of these steps. And there are some other methods that we're going to do in future. So you are going to do the same thing. Okay, any question? So that's topic number 1. Okay, this was section chapter 5.1. Just listing the terms of the sequence. 1 question, 2 parts. Ordinary sequence when the general term is directly given. The other one is recursively defined, if you like. Okay, these are going to be discussed, as I showed you, in 5.7 and 5.8, but we just take a preliminary step here. So that was case 1. And number 2, induction. Okay, the first part of the induction, we give you an equation, an identity to describe it for us. There are some fine popular one. We did it, and you got it over here too. The most popular one is just the first one. Remember, it's a kind of geometric sum, and of course, you are not going to use any formula from geometry. You must use induction only. Okay, that's the power of a number. If you pick any number, you have the other problems. So I'm going to call it part 1. Okay. So the part 1. So basically, you want to prove by induction. Prove by induction. Okay, the first one is this one. We want to prove the power of the given number, 5 cubed, 5 to the 4th. Okay, continue up to the 5 to the n. Okay, this is geometric sum. There is a formula for it. It's going to be this common ratio, we call it 5, 5, 5. It's going to be 5 times the 5 to the n. And it's always minus 5 squared, which is 25 in this case. And it's always divided by 5 minus 1, which is 4. Of course, this would be given to you, but I'm just telling you that if you know that formula, you cannot say that, oh, I know it, this is the formula. No, you have to prove it by induction. Okay, you want to prove this one when n is greater than or equal to 3. That's it. That's the question. Okay, now we're going to solve it. Remember, you have to introduce a predicate, Pn. Pn is the target. What do you want to prove? Pn is this identity without quantifier. You have to write it down, otherwise your proof is not going to be valid. You are going to give us a Pn. Pn not equal to just an expression. Pn is this: 5 to the third, 5 to the fourth, up to the 5 to the n equal to 5 times 5 to the n minus 25 over 4. That's a Pn. No quantifier. Now, what you want to prove? You want to prove that the Pn is true for all n greater than equal to 3. So I should prove, or one should prove, or it should be proved. One should prove that Pn is true. Okay, Pn is true for all n greater than equal to 3. That's the target. Now you have a problem. Any question? If you don't put it into this modeling, your induction argument is going to be meaningful, okay, or meaningless if you like. So now you know what you want. That's the first step of the induction. You have to have a predicate Pn that involve counting numbers. So that's the case, okay? So make sure you set it up correctly. Now you go to the argument, 2 steps, basic part. The basic, you have to prove this one for the basic elements, initial value, least elements of the n. N is equal to 3, so we go with the n equal to 3. If n is equal to 3, substitute on both sides to see if it's satisfied. When n is equal to 3, you get 5 to the third only here. Okay, it's going to be 5 to the third. So 5 to the third must be equal to what? Equal to the 5 times 5 to the third minus 25. Okay, divided by 4. So you work on this side. So this is going to be equal to, it's going to be 5 times 125 minus 25 over 4. So 125, 25, that give 100. Okay, 100 over 4, you simplify it. So that give you 5 times, that's going to be 25, 5 times 25, which is the 5/3. Okay, 5 times 25 is going to be 5 times 5. You know, we don't have to find it even. It's 125. So 5 cubed equal to the 125? Yes. So you prove that your formula works for n equal to the 3. So P3 is true. That is the first step. Any question? We know that it's trivial, but it's not proved yet. Okay. Don't say it's trivial, that, you know, for 5 cubed. No, it's not unless you proved it. So you just substitute the result. Any question? So that's the basic part. Now inductive part. Since you have only one initial value, n equal to 3, this is ordinary induction. If you have more than one initial conditions, it's going to be a strong. It's ordinary, so you fix it at one number first. You see, suppose an integer k greater than equal to 3 is given such that pk is true. Okay, you're going up a building, if you like, you go to the 10th floor. So you stop at the 10th floor and you try to get to the 11th floor, if you like, the next one. Okay, so we assume that such that pk is true. pk is true means identity is true for, okay, pk is true, so you repeat the identity for n equal to the k. So this means you have 5 to the third, 5 to the fourth, up to the 5 to the k is equal to what? Is equal to the 5 times 5 to the k minus 25 over 4. So you do have this one. Now you want to prove it for k plus 1. K plus 1 means you have to go up to the 5 to the k plus 1. Okay, you have this one. Now form the one that you want to find out. Say, oh, that, this is what I want. It's a 5 to the third. This is 5 to the fourth. up to the 5 to the k already, you see, but I want the next step, so I have to add the 5 to the k plus 1. Okay, so this is up to the 5 to the k plus 1. So you have to work on the right to get to formula what? 5 times 5 to the k plus 1 minus 25 over 4. This is the target. So what you're going to do is, you are going to look at this one. You know that this is a pk. pk means this is equal to the 5 times 5 to the k minus 25. So this is going to be equal to, you bring the pk is true, so you have that formula. So it's going to be 5 times 5 to the k minus 25 over 4 already, plus these new terms, plus 5 to the k plus 1. So you have to work on this one, try to make it into what? 5 times 5 to the k plus 1 minus 24 over 25 minus 4. Any question? Just a common denominator would do it for you. So you may think about this one, 5 to the k plus 1 over 1. So the common denominator would be 4. So this would be what? This would be 5 times 5 to the, repeat it, 25 plus 4 times 5 to the k plus 1. Okay, I just did the algebra. This should be this one. You stay to the right, okay? So you multiply, it's going to be 5 to the, this 5 to the first, 5 to the k would be 5 to the k plus 1. Minus 5 times 25, 125. Plus k times 5 to the k plus 1, okay, over 4. Now you combine the like terms. You see, you can call 5 to the k plus 1 z if you like. If you call it z, this is going to be 1z, and this is going to be 4z. 1z and 4z would be 5z, means 5 times 5 to the k plus 1. Okay, or just factor it out, whatever you like. It's like combining the like terms. So it's going to be equal to, okay, these two. This one and this one over here. This is 1 5 to the k plus 1. This is 4 5 to the k plus 1. So we are going to have what? You get 5 to the k plus 1, or 5z, $5, whatever you like it, minus 125 divided by k. Okay, any question? Remember, what are you looking for? You are looking for 5 times 5 to the k plus 1 minus 25. So what we can do is, you can factor out the 5 as is, or just multiply, then factor the 5. It doesn't matter. Okay. If you want to multiply, then factor it, it's going to be, or you can factor it really right away. You can factor 5 out of both of them. If you factor out the 5, this would be 5 to the k plus 1. And that would be what? 125 divided by 4. If you think about it, that's exactly what we want to prove. So you write the full version, remember what it was. So you prove that the 5 cubed, 5 to the 4, up to the 5 to the k, and 5 to the k plus 1 is equal to what? Is equal to the 5 times 5 to the k plus 1 minus 25 over 4. That is exactly the formula for k plus 1. Okay, when it was a k, it was 5 to the k, by n, 5 to the n. It's a k plus 1, and you prove that it's going to be 5 times 5 to the k plus 1. So the conclusion is going to be pk plus 1 is also true. Okay, so we fix it for the k, and we prove it for k plus 1. So by induction, okay, by induction, Pn is true. Pn is true for all n greater than equal to 3, and you're done. Any question? So again, your proof must be consistent. The logic of the argument, actually the setting up, the given formula is going to be your Pn, the one that you want to prove. And you put the basic type, basic part, which is easy. Then you fix it at a K at one level. You fix it at one level and you go up. You go up to the, okay, to the next level. So in order to get the next one, you write whatever you want to prove. You say this is the one. You have to find the sum of the powers of the 5 up to the K plus 1 this time. So you break it in two parts. After the K, you already got it because the formula is given to you. So the rest is going to be a kind of algebra to get these numbers through. Okay, any question? So this is, this is for 5. You want another problem, change it to the 6, change it to the 7, change it to the 9. Everything would be the same thing. Okay, that's type 1. You have these powers of the 1, which is very important for computer science. I give you 1 plus 2 plus 3 up to the n. Okay, I do the square one. You use this one in your field. All the powers. And you have something that you want to estimate, and you will refer to these formulas. So let me just do the C. This tab. The true is also easy. I do the third one first, a couple of them, and I'll come back. So the 2b is, I can do the b first, if one. They're all the same. So the 2b is 1 times 2. These are times, not decimals. 1 times 2 plus 2 times 3. Okay, it's just a product of two consecutive numbers, 1, 2, 2, 3, 3, 4. Okay, up to the n times, okay, it must be n minus 1 times n, it doesn't matter, it's the same thing. Okay, this is given to you. It's equal to the n times n minus 1 times n plus 1 divided by 3. You want to prove that this is true for n greater than or equal to 2. Okay, this is the product of consecutive numbers as we move on. Okay, it's going to be 1 times 2, 2 times 1, 2 times 3 up to the n times n minus 1. And you want to prove that this is going to be always equal to the n times n minus 1, then n plus 1 over 3. Okay, of course, the induction. So introduce the Pn, you see. So the solution of this one is going to be as follows. You introduce the Pn, the important part. You suppose that, okay, suppose the Pn is this fact. Pn is the fact that, 1 times 2, 2 times 3, up to the n times n minus 1. This is equal to the n times n minus 1 times n plus 1. Okay, divided by 3, no quantifier. So one should prove, or we should prove, one should prove that. Should prove that the Pn, okay, the Pn is true. Pn is true for all n greater than or equal to 2. That's now you set up the problem. Okay, we talk about it. You must have something nice, okay, logically sounded to be able to prove it. Okay, are you ready? The basic step. The lowest number that you have is n equal to 2, n equal to 2. Okay, so you substitute to see, and when we get n equal to 2. So when is n is equal to 2, in this part, you see, if you like, you put n equal to 2, that gives 2 times 1. You have only one part, okay? So if n, if n is equal to 2, so this is what we are going to have. We are going to have 1.2 here, and this is going to be equal to, you replace the n by 2 to prove that this is going to be equal to 2 again. So it's going to be what? It's going to be 2 times n minus 1 would be 1 times n plus 1 would be 3 divided by 3. Okay, so I substitute n equal to 2. And that's it. This is going to be 6/3. And the 6/3 is equal to 2. 1 times 2 is 2. 2 equal to 2. So P2 is correct. P2 is true. Okay, so that's going to be the first step. Any question? Now you fix it for K and try it for K plus 1. So inductive part, suppose fix it. Suppose K greater than or equal to 2 is given. Okay, is given such that PK is true. Means you can write the identity for K. Then you have to prove it for one more step. Okay, and algebra will do it right away. Okay, so let's say, what does it mean? Therefore, write the formula for K. This is it. You go up to the K times K minus 1. So that's it. It's going to be 1.2, 2.3 up to the K times K minus 1, or K minus 1 times K. And on the other side, give you K times K minus 1 times K plus 1 over 3. That's a PK. You repeat the formula for K. Now you want it for K plus 1. So this means you go one more step. One more step. Let's see what's going to be this one. Say, oh, note that you are going to add the next term. You see, this is 1, 2, 2, 3, up to the what? You go up to the K times K minus 1. You already got this one. Okay, you already got this one. Now you add the next term. What's the next term? Any suggestion? What's a K plus 1 term? Any suggestion?
K times K plus 1.
Excellent. Yes, that's it. K times K plus 1. You see the two consecutive one. Up to the K is going to be K minus 1 times K, if I can switch it. Okay, K plus 1, the two consecutive one, the previous one is K, K times K plus 1. So you have to prove it is equal to what? Is equal to the, this would be K plus 1, K, this would be K plus 2. So you have to prove that it's equal to the K times K plus 1 times K plus 2. You have to prove it. You cannot write it down here. But you can connect. You see, we say, oh, this is what? This is the PK. So it's like the first part's going to PK. I don't have the PK. K times K minus 1 times K plus 1. Okay, but it's a plus. It's a plus K times K plus 1. See? You start with the given one up to the PK is the one that you have before. Okay, you have an extra term. Now find the common denominator. Remember we talked about it. They stay on the right. They stay on the right. Simplify it. Show that this is going to be equal to what? Is equal to the K times K plus 1 times K plus 2. A common denominator would do it. Suppose this is 1. So it's going to be equal to the common denominator would be 3. So on the top we get the K times K minus 1 times K plus 1. Okay, and this is going to be plus 3 times K plus 1. Okay, I just find the common denominator. Don't multiply it because you lose everything. Factor out. Remember what you want on the top? On the top, you need K times K plus 1 times K plus 2, 3 consecutive numbers. So the common factor is K times K plus 1. k times k plus 1. So factor it out. So we have the k times k plus 1 as a factor. So what's going to be the leftover? A k plus 1 would cancel out. So the leftover here is going to be k minus 1. Okay, that gives you k minus 1. And the leftover over here is going to be just 3 plus 3. You see, automatically you get what you want. So it's going to be the result, it's going to be equal to k times k plus 1 times k plus 2 equal to 3. That's exactly what you're looking for. So you bring the one to the right, so oh, this is it. 1 times 2, 2 times 3, up to the what? Up to the k times k minus 1. Then k times k plus 1 is going to be equal to the product of these 3 consecutive numbers, and that's exactly pk plus 1. Okay, so pk plus 1 is true, means the formula is true when you replace the n by k plus 1. Is going to be true. By induction, okay, by induction, Pn is true. Pn is true for all n greater than or equal to 2. You see, again, the writing part really, the algebra part is just it's just a common denominator to the right for all of them to be able to put them together. But you have to make sure that you write down correctly, especially when you want to add this last term. Okay, you repeat the formula for n equal to the k plus 1. So it end up always with 2 consecutive numbers. One of them must be k plus 1, so the lower one is going to be k. And then you work to the right, okay? You stay on the right to simplify it, and then you arrive at the fact that the formula is also true for pk plus 1. Okay, any question? We give you something short, something, that be practiced, but it doesn't matter, you can do all of them. Okay, the other two are similar. If I cannot do it, I post this, the solution, I have all of them. Okay, but something short, something that gives an idea, those powers of the 5 was a nice one, or this part, because we give you just one of them of this group of 2, but I put everything there so that you can have it. So that's a type 2 question. Type 3 is interesting. This is a type that you are going to do it in future again. So we give one of them. It's going to be a kind of identity. We call it sequential equation. In future, you are going to solve this equation for us. But solution of these equations are going to be the case that we guess what is going to be the solution. Then we prove our guess, if you like. In this problem, this is your job. We give you the solution. You confirm it for us by induction, okay? So this is question number 3, or the type 3 of the induction. You see, they ask you to let this identity, let an is equal to, an is equal to the an minus 1. There are 2 groups. The second one is easier, but we give one of them. You see, this is given to you. Recursively defined sequence, an equal to the an minus 1 plus, and a 2 here. And the first term is also given. You see, we wanted to use induction. We want to use induction to prove the solution is to prove that the sequence that satisfies this identity, an, is simply n squared plus 3n. N squared plus 3n, of course, for n greater than or equal to 1. Okay, so this is the type 3 that we talk about it. It's quite very popular case, application of induction. Okay, and you are going to use it for some very mild. This is very mild of these type of equations. Okay, so there you are. This is it. What's going to be your job? Again, important part is to set up the Pn. The Pn is what you want to prove, but you have to write down. Say, oh, suppose what is going to be the Pn? This is a statement that the An is equal to n squared plus 3n. That's your Pn, no quantifier. So one should prove what? One should prove, okay, one should prove that this Pn is true. Pn is true for all n greater than or equal to 1. That's your job. You see, you have it, and you want to prove that it's An that satisfies that condition. Okay, are you ready? Basic step, replace n by 1. Get the A1 and show that A1 is 4. Okay, so the basic step, if n is equal to 1, what's going to be a P1? You see, you substitute. So A1 is going to be equal to the 1 squared plus 3 times 1. It's like those equations that you know that solution that we tested. So this is going to be 1 plus 3, and 1 plus 3 is 4. So this means A1 is equal to 4. From this formula, A1 is equal to 4. And originally, we know that the A1 is equal to 4 too. So this statement is true. Okay, so the P1 is true. Any question? So you prove that the formula is true for n equal to 1, or the P1 is true. Now, the fun part is you have to fix it for k, and you prove it for k plus 1. Okay, so inductive part. Inductive part, suppose k greater than or equal to the 1, fix it, is given such that pk is true. pk is true means ak is equal to the k squared plus 3k. That's the meaning of pk is true. And what you have to prove? You have to prove by ak plus 1. So you have to prove that ak plus 1 is what? K plus 1 squared plus 3 times k plus 1. So we say, as usual, ak is true. So, or therefore, what is pk? Therefore, ak is equal to the k squared plus 3k. Okay, so what's going to be your job? Your job now is what is ak plus 1? Because you are interested in pk plus 1. Now, how are you going to connect the ak and the ak plus 1 to each other? You connect it by this equation. It's like the strong induction case that we did. Okay, now you say, oh, bad. ak plus 1 is equal to what? You see 1 down is equal to the ak plus 2 times k plus 1 plus 2. Okay, so you go to this identity and you replace the n by k plus 1 because you don't have it anywhere else. So that you ak plus 1, that would be ak, and you substitute for everything. Okay, now you have to work on this and show that this is going to be k plus 1 squared plus 3 times k plus 1. So substitute as usual. ak, what is ak? This is ak, k squared plus 3k. That's your ak. Okay, and you distribute this one, that give you 2k plus 2 plus 2. If you multiply them together, that give you k squared plus 3k, and the 2k would be 5k. Okay, 5k plus 5k plus 4. So you claim that this is ak plus 1. Now, you can show that this is, remember the term is this format. n squared plus 3n, the Pn. So Pk plus 1 would be k plus 1 squared plus 3 times k plus 1. Some people, you try to break it, factor it to get this one, but it doesn't matter. You say that you just do that formula. You say that, oh, note that the one that you want to prove is this one, k plus 1 squared, or k plus 3 times k plus 1. This is ak plus 1. You can square it. That give you k squared plus 2k plus 1. And that would be 3k plus 3. If you combine the like terms, that give you k squared, 2k and 3k, 5k plus 4. So the one that you got over here is exactly what you want to prove. Okay, so this means pk plus 1 is true. Okay, so this means, if you like, so ak plus 1 is in fact k plus 1 squared plus 3 times k plus 1. So pk plus 1 is true. Pk plus 1 is also true. And by induction, you got it. By induction, Pn is true. Pn is true for all n greater than equal to 1 to get the final answer. Okay, any question? So this one is the part that you got to be careful is you are not going to get it right away. You see, it's going to be a kind of a polynomial type. You can break it, factor it, to get to that one, but why not? This is your target. So you do it the other way around. You simplify this one to show that it's the same as the k squared plus 5k plus 5. So basically, you know that you already got the pk plus 1. Okay, this is number 3. Number 4 is better because you see it. You don't need any extra job, if you like. This is a kind of polynomial type. Number 4 is more popular. It's a geometric type, and it's used mostly more than this one. So we try that one too, but we give you one of them, either of this type or the other one. It's going to be both of them are going to be not a very difficult one, okay? Because you cannot do the difficult one in reality. You can only do this type of problems. Okay, any question? Again, the format is something that we repeated over and over and over. Let's do the next one so that you see how it's going to be easier when it's handling with this geometric one. Okay. Number 4, the sequence is, this is the type of sequence that we get it in your next quiz and the test, not this test. Because we have, you invest money in the bank, this is the way the bank would give you the interest. So you have a couple of problems on this one. Okay, so let's see what's the problem. The problem is you want to check the equation of this sequential relation, if you like. So you have the an is equal to the 3 times an minus 1. Then the number is 2. The reason that it was a little bit more involved for the other one was you have 2n plus 2. In this case, we have only 2. That's easier. Okay, so this is the case, and the a1, of course, is given to you. A1 is 2. So they ask you to use induction. Use induction to what? To show that we want to show that the an is of this form, is a geometric form, 3 to the n minus 1. Of course, for all n greater than equal to 1. This must be given, It's not given, but it's going to be given to you. Okay. So you have this equation, we call it, and you want to prove that the solution of this equation, an is 3 to the n minus 1. Again, set up the Pn and start arguing about that one. Okay, so the solution, we need to have the Pn. You see all of them by now, you know it. depend on the Pn. That's why I emphasize that if you don't give us the Pn. So what are you talking about? Some people, they just talk about the P1, PK plus 1, but when you check your solution, you see there is no Pn. So you have to start with the Pn so that you'll be able to talk about P1, P2, okay? So Pn is just the statement you want to prove. So suppose Pn is this that you want to prove. You want to prove the An equal to the 3n minus 1, no quantifiers, okay, that's your Pn. So you have to prove, or one should prove that a Pn is true. Okay, Pn is true for all n greater than equal to, you see. Now we set it up correctly. That's it. We check it for n equal to 1. 3 minus 1 would be 2. You already got it. Then we assume that it's true for k. So this means ak is 3 to the k minus 1. Then we connect ak plus 1 and ak by this equation. And we substitute, we get it. Okay, so that's going to be the procedure. So the basic part, n1 and the p1. So if n is equal to 1, we go to this equation, we get the a1. a1 would be 3 minus 1, which is equal to 2. So a1 is equal to 2 by this formula, and originally is 2 as well. So p1 is true. P1 is true. Any question? Fix it for k and prove it for k plus 1. So inductive part, fix it. If k greater than equal to 1 is given, such that is given such that pk is true. Oh, so bring what do you mean by pk is true? Pk is true means ak is 3 to the k minus 1. You just note this one. We say so ak plus 1 is 3 to the k minus 1. So I should try to find the ak plus 1. How we're going to connect? You connect it by the equation. It's the only part that use this equation, okay? So we say, oh, but I know that ak plus 1 is equal to 3 times 1 dot. See, that's it. 3 times a minus 1. It's going to be 3 times 1 down, 3 times ak. Okay, 3 times ak plus 2. But the ak, you don't have the ak. So substitute is going to be 3 times 3 to the k minus 1 plus 2. Distribute it. The base are the same. It's going to be 3 to the k plus 1 minus 3 plus 2. So this is going to be 3 to the k plus 1 minus 1 ak plus 1. And that's exactly what you want to prove. Remember, this is your formula, 3 to the n minus 1. 3 to the k plus 1 minus 1. 3 to the k plus 1 minus 1. So pk plus 1 is true. And by induction, Pn is true. Pn is true forever. True for all n greater than equal to 1. And you're done. Okay, any question? So this format is easier. I mean, both of them are easy, not easy. But the polynomial type, you don't get it right away. You see, you have to go back and do a little bit more operations, algebraic operation, but with the exponential one, automatically we get it. So be careful. But some people, they don't use parentheses here, they miss it. they don't use parentheses, so they multiply 3 only by 3 to the k. Then there is going to be left over that they cannot fix it together. I've seen this is where they know when they get lost, if you like, in the proof. So get the parentheses, make sure you multiply 3 times 3 to the k and then 3 times 1. So we'll be able to take care of it. Okay, so that's type 3. Any question? Now the type 4, number 5, that's that famous theorem of the Litter-Fermat theorem, which is easy to handle. Okay, we give you one of them, number 5. I put all the possibilities here. It's going to be only one of them. Number 5, Fermat theorem. For example, this the first part is one of the assignment in your book, I think. You want to prove by induction. Prove by induction. Again, one of these. What you have, part 1. You want to prove that 2 to the 2n minus 1 is divisible by 3. By 3 for all, they say 0. They can go with the 1, but they ask for 0. It's okay. For all n greater than or equal to the 0. That's it. You say this problem in your book, I just want to explain it. You can simplify it. 2 to the 2n is going to be, you see, note that. 2 to the 2n is like 2 squared. You know, it can be done as is, but I want to give you something general. So you can write it down as 2 squared times n. 2 squared would be 4. So it's going to be 4 to the n. That's easier to handle if you like. Okay, so 2 to the 2n minus 1. That's the format of that general theorem that you have. You want to see it. Okay, so you want to prove that 4 to the n minus 1 is divisible by 3. Is divisible by 3. So this problem is when it's a 4, it's a 3. When it's a 5, it's a 4. 7 is a 6. So that gives you better understanding of this. We call it the Litter-Fermat theorem. Okay, that's it. Set up the Pn. So I just switch this one. I worked with 4 to the n minus 1. So the solution is going to be, so we go with the Pn. Suppose Pn is going to be just a statement of what? 4 to the n minus 1 is divisible by 3. No quantifier this time. So you should prove, or I should prove, one should prove that Pn is true. Pn is true for all n. They start with the 0. In your book, they start with the 1, but the 0 doesn't matter. Okay. So go for the basic statement. The basic part, you replace the n by 0, and you show that 4 to the 0 minus 1 is divisible by 3. So if n is equal to the 0, n equal to the 0, then what we have over here, okay? So we get 4 to the 0 minus 1. 4 to 0 is 1, 1 minus 1 is 0. 0 is divisible by every number. Divisible by 3. If you start with the n equal to 1, as we did for all the other problem, that gives you 3, which is divisible by 3. Well, we stay with this one. So P1 is true, P0 is true. So you have to start with the initial condition. Okay, any question? Fix it for K and get it the next one. Okay, so suppose inductive part. That was the basic part, inductive part. Suppose K this time greater than or equal to the 0 is given, such that, okay, is given such that what? Such that pk is true. So you write down what you mean by pk is true. pk is true means 2 to the k minus 1 is divisible by 3. And you know what does it mean, divisibility, okay? So you can say that, so 4 to the k minus 1 is divisible by 3. Divisibility by 3 means there is a t, for example. There is a t such that 4 to the k minus 1 is equal to the 3t. Talk about two different methods, whatever you like. You want to go with your book, just find the 4 to the k. That's going to be 4 to the k equal to the 3t plus 1. But remember, you want to work with the 4k, okay, pk plus 1. So you have to find this one. You say, oh, note that. This is the one that you want. 4 to the k plus 1 minus 1. You want to prove this is a multiple of 3. You just, you know, you break it into parts. It's going to be 4 times 4 to the k, then minus 1. You bring the 4 to the k from here. So it's going to be 4 times. You substitute 3t plus 1 minus 1. Distributed, that give you 12t plus 4 minus 1. So this would be 12t. 4 minus 1 would be plus 3. You factor out the 3. That give you 4t plus 1. You may call it 3t1. Okay, remember you want to prove this is also divisible by 3. So there you are. 4k plus 1 minus 1 is also divisible by 3. So this means 4k plus 1 minus 1 is divisible by 3. So pk plus 1 is true. Okay, so this means pk plus 1 is also true. By induction, okay, by induction, 4 to the Pn is true. Pn, by induction, Pn is going to be true. Okay, for all n greater than or equal to the 0. Again, this is a very easy induction, really. You can't miss it to get these numbers. Okay, and all of them, you see, order of the proof. Order of the proof must be logically correct, okay? The others are the same. I have the solution of all of them. I posted for you. Okay, so these are all ordinary induction. We give you one, a strong one. I want to make sure I give you one. And that's a number 6 and 7. See, as you can see, it's going to be all together with the sequence 6 questions, okay, and 1 each. Okay, let's give you the strong one. Then I post the solution for all the others. You know, we just change the number. That's 4, 7, and then you can check it for yourself. Okay, that's the strong one. A strong one, it takes a bit more time, and again, you got to be careful. Remember, the difference between the strong and ordinary one is, in the case of the ordinary one, you have one initial condition. So you have to prove that basic step in one level, one step only for one value of n. But in a strong induction, you are going to have more than one basic step. Okay, so you may have to prove the P1 and the P2 or P3 is prove. And then you have to modify it when we get to the K. We talk about it, then let me show it to you. For the time being, we can do on this sequential type. So if you give it one sequence and its solution, in future, you are going to be able to find the solution yourself. There you are. It's very standard question. And if you write it down correctly, the algebra part are all the same. This is 7 times an minus 1 minus 10 an minus 2. This is true when n is greater than or equal to 2. And you have two initial conditions, a0 equal to the 0. In your book, they start with the 1 or 2, right? Doesn't matter, I start with the 0 here. You see, this equation is given to you. We did write, remember, several terms of this sequence. You can do that, but that not would be with the proof. We want to use induction to show that, okay, so what we want to show that, this is it. Show that the solution is an is equal to the 5 to the n minus 2 to the n for all n greater than or equal to the 0. Okay, it's like number 4, but number 4 is just ordinary induction, but this is going to be the strong one. Okay, now how are we going to check it? Go with the Pn first. Pn is this statement, and you have to write it down. Okay, so suppose Pn is this statement, the statement that an is equal to the 5 to the n minus 2 to the n. No quantifier, remember. That's Pn. What you should prove? 1 should prove that Pn is true. Pn is true for all n greater than or equal to 0. That is the statement of the problem that you want, to get it. You prove it. Okay. 2-step basic one. That's a basic step. You have two numbers to check. You see, you have the n equal to the 0 and n equal to 1. So that's the first difference between this and the ordinary one. So we go for it. If n is equal to the 0, you test the formula for the 0. So that give you what? That give you a0 equal to the 5 to the 0 minus 2 to the 0. It's going to be 1 minus 1, which is 0. So a0 equal to the 0, which is true. a0 equal to the 0. You have to check this one. Okay, so this so far means P0 is true. But you're not done because it's a strong induction. Check the other one. If n is equal to 1, test the formula for 1. a1, 5 minus 2, which is 3. So a1 is equal to 3, which is a fact. So this means P1 is also true. That's a basic step. As you can see, you have one more step to check when you compare it with the ordinary one. Now you have to fix it. The fixing one, you got to be careful again, because previously you fix it for k and you go to the k plus 1. When we say fix it for k going to the k plus 1, this means, if you can take any number, you should be able to get to the other one. So, for example, if k is equal to the 0, then for the other one, since you have one initial condition, so one fixed number would be enough. But over here, you should be able to get back to the 2 previous terms, not just 1. That's why you have to modify. The modification was this one, remember? So you suppose that k greater than or equal to 0, okay, is given such that that was the one we talked about. Everything up to the k. This means such that P0, P1, that Pk minus 1, and the Pk are true. You see, you have to guarantee that you can go back as many times as you like. You see, not only the k, but also pk minus 1, pk minus 2. Why? Because you have to be able to connect. You see, you need ak plus 1 now. How are we going to find the ak plus 1? You see, you go to the formula. Ak plus 1 would be 1 dot ak and the ak minus 1. So you should be able to go back twice. You should go back to the pk and the pk minus 1 to recover the ak plus 1. That's why you need to expand the assumption of the induction. Any question? When it's a straight ordinary one, just one term is enough, but not this one. Okay, you must have it big enough. If you need, you go back as many times as you like. In this case, you go back twice because you have two initial conditions. Okay, so suppose k is given to you such that everything up to the k is true. So if everything up to the k is true, so remember in the other one, I just saw pk is true. So pk minus 1 and pk are going to be true. So you write it down. What do you mean by pk minus 1? This means your formula is true for ak minus 1, pk minus 1. That gives you 5 to the k minus 1 minus 2 to the k minus 1. And it's true for pk, ak equal to the 5 to the k minus 2 to the k. You see? Then, note that how are we going to bring the k plus 1 for us from the equation? ak plus 1 equal to, go back to the equation, it's given to you, see? It's 7 times the previous minus 10 times the other. So it's going to be 7 times 1 down, ak, minus 10 times 1 down again, ak minus 1. You see, now you have the ak and the ak minus 1, you can substitute. That's why we need 2 of the previous assumption, if you like. So now the rest is going to be algebra. It's going to be 7 times ak, this is ak, 5 to the k minus 2 to the k, minus 10 times ak minus 1 is going to be 5 to the k minus 1, minus 2 to the k minus 1. You have to simplify it and arrive at what? 5 to the k plus 1 minus 2 to the k plus 1. So it's going to be algebra. You stay to the right and you distribute it. It's just a coefficient, okay? It's just going to be coefficient. It's not going to be doing anything to the base of the powers. So it's going to be 7 times 5 to the k minus 7 times 2 to the k minus 10 times 5 to the k minus 1, negative positive, plus 10 times 2 to the k minus 1. See, this is the way you distribute it. So you have to put the 5s and the 7s, 2s together. That's 5 to the k. This is 5 to the k minus 1. You factor out 5 with the lowest power, which is a k minus 1, always. Over here, the number is going to be 7, but you have the leftover of the 5, because that's a 5 to the k. This is k minus 1 power up. Okay, and here is going to be minus 10. Minus 10. Any question? Now, the other parts, you have the power of the 2. So the lower power of the 2 would be 2 to the k. So we are going to take out, we go with minus, because the final answer is 5 to the n minus 2 to the n. So you take out the 2 to the k minus 1. Over here, we get the 7 and extra power, 2. And over here, we get the negative 10 again. Simplify. That gives 5 to the k minus 1. This would be 35 minus 10, which is 25. And that's going to be minus 2 to the k minus 1. And this would be 14 minus 10. Okay? It's going to be 14 minus 10, it's going to be 4. 25 is 5 squared, so it's going to be 5 times k minus 1. Remember, you want this one to be 5 to the k plus 1. 5 squared, and this is going to be minus 2 to the k minus 1, 2 squared. If you add the powers, You got it. There's going to be 5 to the k plus 1. And this is going to be 2 to the k plus 1, which is ak plus 1. That's a pk plus 1. I'm sorry. This is, so when you multiply with the same base, 5 times 5, you add the powers, k minus 1 plus 2 would be k plus 1. Then the base is 2 to the k minus 1 plus 2, k plus 1. That is exactly pk plus 1. pk plus 1 is true. Okay, by induction, Pn is true. By induction, Pn is going to be true for n greater than or equal to 0. And then you're done. Again, it's a standard argument for this type of problems that you have. When these algebras, make sure you get it all right to get these numbers done. Okay, that's number 6, a strong induction. The next one is also very similar. I have the solution of all of them that I posted for you tonight. So try to get it yourself, otherwise check your solution. You must feel easy about, relax about the application really of, how to set up these formulas. That is the way, okay, that's the way we do it. These type of problems, okay? They are very, when you get the idea, it's a kind of routine problems really, but you have to feel it, understand it, this notion, how we connect together, especially look at this. You see, we prepare it, our AK and the AK minus 1 here nicely. Okay, that's going to be AK and the AK minus 1. And then what we did is we just went back and we put them together. Okay, because the formula give you the terms in terms of the AK and AK minus 1. So we go back and we put them together, and nicely, automatically, it must come out if you like, to get numbers. So that is the induction part that we're going to have. We try to give you something short, but we give you one from each, really, that's one. And as I told you, we repeat it even on the final, because this is important case. Okay, so that's it. Any question? So I post the test on the, okay, as usual, on the Canvas. Would be available 11:10 as usual, the lecture hour. And when you're done, you just put them together and return it to the Canvas yourself. As time being, you don't need to come to the Zoom. Okay, you can email me. If I'm done, I come back. I'll go on the Zoom myself. If you have any question, you can email me. That would be better. So I don't want you to confuse you. So be ready. Just take it from the Canvas yourself. Just return it, but make sure that this takes time. You have to have a good concentration on these problems. Otherwise, it would be useful really for your field. It's not bad. It's a nice mathematics. Okay, that's it. Any question? So take care and good luck with the test on Wednesday. I post the solution of your quiz and the grade by tomorrow, but I try to post the solution first because I wrote the solution so I can grade the papers. Okay, this is going to be the test day, so no assignments going to be due. You're just coming for the test. Okay, have a good one. Take care. Anything, you just email me. I have to go to my next class. Bye-bye.
Thanks, Professor.
Thank you. Bye.